Since the introduction of anesthesia gases and vapors into clinical practice in the 1850s, we have struggled to find a tool that provides us with good information about depth of anesthesia. We're always concerned that our patients were either overdosed or underdosed. In the 1960s, a concept evolved known as the minimal alveolar concentration, or MAC, that came from studies of drug potency versus movement, and that has evolved to be the principal tool that most anesthesiologists use in their clinical practice all day, every day to assess anesthesia depth. Much of the time, this is actually quite misguided, but nevertheless, it is a fact of life and it is probably the best measure we have. These tutorials will look at MAC, the history of MAC, the variants of MAC, and how to use MAC in your clinical practice. And I'll follow it with a discussion about controversies regarding MAC. The first one is about MAC history. Fundamentals of Anesthesiology with me, Pat Nelligan. Understanding gases and vapors. The MAC, or Minimal Alveolar Concentration, Part 1. In the previous tutorial, I introduced the concept of MAC, and then I correlated it with drug potency in the guise of the oil-gas partition coefficient, and then we looked at the coefficients for various different volatile agents and gases. And I explained why potency is less important than solubility. In this tutorial, I'm going to discuss the history of development in monitoring adequate depth of anesthesia and the development of MAC, and why MAC became the de facto monitor of adequate depth, why MAC must be adjusted for age, and why MAC must be individualized from a population-based number. Let's start with the history of MAC. If we go back to the 1950s, we had a series of volatile anesthetic agents such as ether, halothane, cyclopropane, and methoxyfluorine that all appeared to work well. But they were being compared using vague language like stronger, lighter, or deeper anesthesia. We didn't have a rigorous way of describing dose effect relationship, and there was no common unit of potency. To do that, you need to have a measure of how much anesthetic the patient is actually receiving, and you had to link that measurement to a reproducible biological effect. In the late 1950s, infrared gas analyzers became available so that all of those volatile and gas agents which absorb infrared light at different wavelengths could have their concentrations measured on inspiration and expiration. And although those machines were relatively crude and they were influenced by carbon dioxide, they were nonlinear in response, and they were insensitive, we could now continuously measure end-tidal anesthetic partial pressures continuously. And we knew that if end-tidal gas levels were held continuously, the arterial and brain concentrations equalize. That's the alveolar brain spinal cord blood steady state that I mentioned previously. Consequently, the end-tidal vapor concentration could be used as a surrogate for brain concentration. In terms of defining adequate depth of anesthesia, we had a problem. EEG was and indeed remains controversial. Autonomic responses, heart rate and blood pressure are unreliable. And there were other things like pupil diameter, muscle tone, all non-specific. The patient appears to be, for want of a better term, asleep, but how can you be sure? All of that left at the time one unambiguous sign of adequate depth of anesthesia, that the patient did not move to a surgical stimulus. So how could this be done? It was all about concentration versus movement, measuring the end-tidal anesthetic concentration, holding it stable for long enough for equilibration, applying a standardized noxious stimulus, and then recording whether or not there was movement or no movement. So let's go back to 1963, and the hero, I suppose, of this story, the main character, was Ted Eger. He was 32 in 1963 and working at UCSF with a group of colleagues looking at anesthesia potency in dogs and humans, and the term that this group coined was MAC. This particular paper, published in Anesthesiology, was the first mention of the word MAC by Eger and his group. It was actually a comparator study that looked at a now forgotten volatile agent, halopropane, versus halothane, which was the standard vapor back then in 1963, and it was a study of dogs. And I want you to read the first definition of MAC. We defined this common index as the minimal alveolar concentration in the alveolus required to keep a dog from responding by gross movement to a painful stimulus, such as tail clamping or varying electrical currents applied to sensitive mucous membranes. This is not MAC as it was subsequently refined and defined, but it was the same group who provided us with the more modern definition. Their landmark paper in 1964 established the concept of MAC in humans, and I believe that all anesthesiologists should be aware of this paper and you should read it, but to make it easy for you, I'm going to go through it now. It was a study of 68 surgical patients ranging in age from 17 to 78, divided into three groups. They were all pre-medicated with atropine. Group A were inhalationally induced with a combination of halothane and oxygen. Group B were pre-medicated, and they were also given 8 to 15 milligrams of morphine subcutaneously, 1.5 hours pre-op. And then they got inhalational induction with halothane and oxygen. And Group C were given inhalational induction with halothane, oxygen, and nitrous oxide, and nitrous oxide was maintained at 70 to 75% inspired. After induction, the larynx was sprayed with 1 to 2 mils of 5% cocaine, and then the patients were intubated without neuromuscular blockade. End-tidal halothane samples were then collected. There was obviously no blinding in this study. All of the patients appeared to be asleep, and a specific target was set for end-tidal halothane to produce a light surgical plane of anesthesia, and that was held constant for 10 to 15 minutes prior to surgical incision. So one presumes that they had arrived at steady state. They looked at the exhaled percentage of halothane that they deemed necessary to prevent a muscular response to the surgical skin incision, and they defined that as MAC 1, 1 MAC. If there was no movement, the patient was above MAC 1. If there was movement, the patient was below MAC 1. Now, 4 subsequent patients, Group D, received electrical stimulus at 30 to 40 volts that was repeated until movement was not detected. And in 2 of these who had nitrous oxide, the latter was stopped and the cycle was started again. So this was a study of progressively increasing the dose. It wasn't a study of a specific dose. And here are the results. So we have 3 groups: halothane and oxygen, halothane with pre-medication of morphine, and halothane with nitrous oxide. And on this legendary chart, we can see these 3 groups, A, B, and C. On the bottom line, on the x-axis, we have the alveolar end-tidal concentration of halothane ranging from 0.1 to 1.1%. Any upward deflection means the patient moved. Any downward deflection means the patient didn't move. And you can see as the concentration goes further to the right, fewer patients moved. Here is the 50% movement line. At this point, 50% moved and 50% of patients did not move. For Group A, that point was at end-tidal halothane of 0.74%, what we now know as the MAC. It occurred at 0.69% in Group B, the morphine group, and at 0.39% in Group C, the nitrous oxide group. Putting it together, that means that morphine pre-medication reduced MAC by 7%, and 70% nitrous oxide reduced the MAC by 61%. Note that the range from everybody moving to nobody moving was quite narrow. There was no movement at 0.78% in Group A but all but one patient moved at 0.73%. This means that the dose response curve for the volatile agent is extremely steep, with a very narrow range between everybody moving and nobody moving. And I want you to remember this curve for future reference. It's extremely important. Following the human study, Eger and colleagues realized that they were onto something. Hence, MAC took center stage in this paper from 1965. Again, this was a dog study, and they showed that by using MAC, the fractional concentration in dogs required to render them immobile fell in hemorrhage, hypotension, metabolic acidosis, and hypoxia. But critical from that time was the first real definition of MAC that we understand. I'm going to read this to you. MAC was taken to be the concentration midway between the highest concentration allowing and the lowest concentration preventing a positive response, and that was movement. This established the concept of MAC and movement. In his earlier papers, Eger was actually trying to correlate MAC with cardiovascular depression. What the investigators did not know at the time was that immobility was a spinal, not a cortical effect, and this has led to an incorrect belief by many anesthesiologists that MAC equals unconsciousness. It does not. It's about movement. Also, it's interesting that, as far as I'm aware, MAC is the only proprietary term used in medicine to replace a well-known pharmacological term, in this case the EC50, the effective concentration 50. Just to make this clear, the MAC is the EC50 for movement in response to a surgical incision. This is what MAC is. It is all it ever was and all it ever will be. It is not about loss of consciousness, amnesia, or blocking the adrenergic response. It is all about movement. Let me quickly explain what the EC50 is. Most drugs are studied using the ED50, the effective dose 50, or the median effective dose. So a fixed dose is administered. That could be, for example, propofol. And the investigators look at how much propofol is needed to render 50% of patients unconscious. Volatile anesthetics are delivered in a different way to target alveolar brain concentration or partial pressure in real time. We measure this as end-tidal concentration as a percentage. So we're continuously measuring the drug and we're targeting a concentration, not a specific dose. So the MAC, as we currently understand it, is the EC, the effective concentration 50. Let's move on to 1969. MAC is not the same for every patient. Age matters. By 1969, Eger's group had determined that MAC varied with age. It was highest in newborns and lowest in the elderly. And this led to a problem. If the MAC is different at every age level, how do we standardize it and at what age? Now, I'm not sure what happened in 1969, but presumably they all huddled together over coffee or a cocktail and decided to standardize the age of MAC at 40. This is probably because the average age in the Eger studies was 40. And as a consequence, for all of subsequent history, MAC has been conventionally reported at the age of 40. There is no single MAC value. Over the course of 30 years, from the first MAC paper, dozens of studies were published looking at minimal alveolar concentration, and as more agents became available, enflurane, isoflurane, sevoflurane, desflurane, the MAC values for all of those agents was determined, and many studies were done on those agents. And Mapleson assembled all these data into this landmark meta-analysis in 1996. And to me, this is the definitive text on the MAC of the agents that we use. And what was truly impressive was that the relationship between MAC and age is remarkably consistent. And this provides us with one of the greatest rules of thumb in anesthesiology. Using that benchmark, 40 years of age, above that age, MAC decreases by 6% per decade. Below 40 years of age, MAC increases by 6% per decade. Let's look at that for various different volatile agents. Here is the MAC at age 40, and you will immediately notice that the MAC of sevoflurane was now benchmarked to 1.8%, and for desflurane, it was 6.6%. For iso, which we still use, was 1.17%. When you went up to an 80-year-old, the MAC of sevoflurane dropped to 1.4%, and down to a 1-year-old, it was approximately 2.3%. These are not necessarily the numbers you would quote back to me, and I'm going to briefly show you the charts from the paper as they give us tremendous information about these agents and also how much MAC falls with nitrous oxide. These figures are from Mapleson's meta-analysis. This is the chart for isoflurane. The end-expired volatile is on the y-axis. The age is on the x-axis. And those lines that are pouring down the middle of the chart are the age MAC lines. They're almost in parallel, as we've already seen. We will draw the 40-year-old line in purple and a red line that intersects the y-axis at the exhaled dose that establishes the MAC of isoflurane at 1.17. By moving across to the right-hand side, you can see the impact of nitrous oxide and how it reduced the MAC of isoflurane. 50% reduced the MAC to below 0.6% and 67% to about 0.4%. This is the chart from the same paper for sevoflurane. Again, the 40-year-old standardized MAC and the MAC intersection that established the MAC of sevoflurane at 1.8%. With 50% nitrous oxide, that was reduced to 0.9% and 67% nitrous oxide to about 0.6%. Finally, we have desflurane on the same two lines. The MAC for desflurane was now established at 6.6%. With 50% nitrous, that reduced to 3.4%, and 67% nitrous to 2.4%. These are substantial reductions. Why is this? Well, the reason is because MAC is additive. Half a MAC of one agent plus half a MAC of a second agent is 1 MAC. Although adequate depth of anesthesia cannot be achieved with nitrous oxide alone because the MAC of nitrous oxide is 104%, 70 to 75% nitrous oxide was added to volatile agents traditionally. And when I started anesthesia, this was the way everybody did it. And there was good reason. The first one was that MAC is seriously reduced. And because nitrous oxide has lower solubility than older volatiles, there was quick onset and offset times with the lower dose of volatile that you had to give the patient, some of which were quite long acting, such as halothane. Nitrous oxide, even today, is really inexpensive versus other volatiles, but back in the 1980s and the 1990s, Sevoflurane, desflurane, and to a lesser extent isoflurane were still under patent and they were very expensive. And at the time, circle systems were not in wide use, so it wasn't possible in many operating rooms to recycle volatile agents until the 1990s. Finally, why does everybody think that the MAC of sevoflurane is 2% and desflurane is 6%? The reason for this is that the early literature quoted these rounding numbers and they caught on. The sevoflurane of 2% was slightly inflated because many studies used nitrous oxide and younger subjects. The meta-analysis sorted all of this out. It corrected for age and it corrected for other things like nitrous oxide and normalized it. And as a consequence, the precise consensus values today are at the age of 40, sevoflurane's MAC is 1.8% and desflurane's is 6.6%. And for the remainder of these discussions on MAC, these are the numbers I am going to quote. What MAC is and what MAC is not. Key thing to understand is that MAC is a median population-based number. That number that's in your textbooks is the EC50 for the population. That is not your MAC, that's not my MAC, and it's not the MAC of any of your patients. Every individual has an EC50 for movement. Now, we talk about that as the patient's MAC, but that's not technically correct, but that's what everybody does. We cannot measure it directly, and we do not know it in advance. So the population-based estimate is used to approximate it. And there is a problem with terminology. The MAC, as defined and described since 1965, is not the minimum concentration for anything. It is the median exhale concentration across the entire population. Remember that there is going to be tremendous scatter along that line, so age is really important, but keep in mind that every single person has an end expiratory value of volatile agent at steady state that stops movement that may not line up with the population-based MAC. And that MAC number for that age represents the point where 50% of patients will inconveniently move following surgical incision. Cue lots of humiliating sarcastic comments by the surgical team. What that movement means with respect to depth of anesthesia will be covered in the next tutorial. Finally, MAC is not a property of the vapor alone, it's a property of the patient vapor system. And when we are referring to MAC on an individual patient basis, we really should be talking about MAC fractions or Fmac. MAC is not measured, end-tidal anesthetic concentration is. MAC is a population reference, and tidal anesthetic concentration is a surrogate for brain concentration, and the Fmac is a normalized pharmacological effect. The Fmac is calculated from the end-tidal anesthetic concentration divided by the age-adjusted MAC. So the end-tidal concentration is what we measure, the MAC is what we reference, and the Fmac is what we interpret. Now let's review this tutorial. In this tutorial, I discussed the history of developments in monitoring adequate depth of anesthesia and how MAC became a universal concept. Why MAC should be considered a population-based number and adjusted for age by dividing the end-tidal anesthetic concentration by the age-adjusted MAC. Next time, we're going to discuss the variants of MAC. The MAC bar, MAC endotracheal intubation, MAC awake, MAC amnesia, MAC and the EC50 versus the EC95, and then MAC and neuromuscular blockade. I'll see you then, and I guarantee you'll learn something.